I'm Anil Kumar. Let me first thank all my subscribers for posting excellent questions. I've combined few questions from my subscribers here to solve in one particular video. We'll talk about a standard method to apply Lagrange multiplier and solve optimization questions. The question here is, use Lagrange multipliers to find the indicated extrema. Assume x and y to be positive. So we have four different functions here with given constraints. In general, we'll write function as f of xy. We are treating two variables, constraint g of xy. Okay. Now, when we say use Lagrange multiplier, what do we mean? We're actually looking for values of x, y, and the multiplier lambda such that the gradient of the function, so we are looking for a point here, right, is equals to lambda times the gradient for the constraint g x0, y0. So that is what we are looking for. You can think this as, those who are not familiar with vectors may think this as the slope of the normal. Okay, so slope of the normal will be same at the optimum value, right? So the strategy which is going to be followed for all the four examples will be kind of like this. So what we will do here, since we have two variables here, we'll equate the partial derivatives with, as per this equation, lambda g of x, right? F of y as lambda g of y. And then we'll use the constraint, which is g of xy equals to k, to find x0, y0, and lambda, right? So that is the strategy which we are going to adopt. Now, I hope that's absolutely clear. So let's take examples one by one and see how this method can be applied very easily. So the first example here is to maximize the function fxy equals to xy. The constraint here is x plus y equals to 10. So we'll always consider this to be the function in terms of these two variables and constraint g of x plus y, right? Now, so from here we are given that the function fxy is equals to xy. That means f of x is equals to, now, partial derivative of xy with reference to x. So y is treated as a constant, so you get y here. F of y will be equals to x. So this is what we've done for the function. Now for the constraint, g of x will be equals to 1 and g of y is equals to 1, right? Derivative of this. Now from the equation, which is, we have to write the gradient for f of xy equals to lambda times the gradient for g of xy. This is, they have the same normal at optimum value, right? So we are finding the critical number by doing so. That is Lagrange's equation, right? So when you equate this, you get y equals to, we get y equals to, that is f of x, lambda times this. This is lambda times 1, okay? And here you get x is equals to lambda times 1. Is it okay? So we get our equation. These are the two equations. Now these two equations, which says the value of y is lambda, the value of x is also lambda, will substitute in the constraint itself. The constraint is x plus y equals to 10. Now if I substitute, now here see y equals to lambda and x is also equals to lambda, correct? So if I substitute these values here, I get the multiplier lambda plus lambda equals to 10, or we get 2 lambda equals to 10, and that gives you lambda as 10 divided by 2, which is 5, correct? So we got the value of lambda. Since we know the value of lambda, we can find both x and y, correct? So we can write y equals to lambda, that implies, this implies, from here we can write the values for lambda equals to 5, and so we can say that y is equals to lambda, which is 5, and x is also equals to 5, correct? And therefore the maximum value will be at f of 5, 5, and it is x times y, right? So that means 5 times 5, which is 25. Do you get an idea? So the point is 5, 5, right? And the maximum value is 25. So that is how we can solve each and every question. So here we found that x is equals to 5, y equals to 5, and lambda is equal to 5, correct? And the maximum value is at 5, 5, which is 25. So go through this process. We are going to repeat it again and again for the other 3 parts. You can actually pause the video, try those 3 on your own. I hope that helps. Now let's take up the next example. Now here is our second example. We use Lagrange multipliers to find indicated extrema, and we are assuming that both x and y are positive. Now this time we have to minimize the function x squared plus y squared, and the constraint is x plus y equals to 4. So we are given the function f of xy as equals to x squared plus y squared. We can take partial derivatives here. So f of x is equals to 2x, and f of y, the partial derivative with reference to y, is 2y. Correct? As far as the constraint is concerned, we can write g of x is equals to x plus y minus 4, and sorry, xy I should have written. This is in 2 variables. So g of x is 1 here, right? And g of y is also 1. So when you do partial derivatives, the other term is considered to be a constant, right? Now we'll follow the Lagrange's multiplier, and that is to say that f of x is equals to lambda times. So we'll do f of x is equals to lambda times g of x, correct? And that means that 2x is equals to lambda, and that means x is equals to lambda by 2, correct? Similarly, f of y is equals to lambda times g of y. That means 2y is equal to lambda times g of y, which is 1, and so y is also equals to lambda by 2, correct? Now the constraint, which is g of xy, is given to us as x plus y equals to 4. Now in this, we'll substitute the values of x and y, which we just found, correct? Which are these 2 values, right? And then we'll find what the multiplier is. So x plus y equals to 4 means we could write lambda by 2 plus lambda by 2 equals to 4, or that is lambda equals to 4, right? So half of half, that means 2 over 2. So lambda equals to 4. So once you know what lambda is, we can find what x and y are, correct? So from here, x is equals to lambda by 2, which is 4 over 2, which is 2. Similarly, y is equals to lambda by 2, which is 4 over 2, which is 2, correct? So we have both x and y as equal to 2. Now we can find the minimum value. So this is a critical number, correct? It could be maximum or a minimum, right? That's very important to understand. Well, let's find the value of this function at 2, right? So if I write 2 and 2, I get 2 squared plus 2 squared, which is 4 plus 4, which gives me the value of 8. So that becomes the value for the function when I'm considering the values of x and y as 2 and 2. Now if I don't consider 2 and 2, then let me check whether it is really a maximum or not, or minimum or not, right? So let's check. So what we will do as a part of checking is that we can take, since this is the constraint for us, we can take some other values of the function. So instead of 2 and 2, if I take y as 1, let's say y equals to 1, then x is equals to 4 minus 1, which is 3, correct? So if I take these two values, then what is f of 3, 1? It is going to be 3 square plus 1 square, which is 9 plus 1, which is 10, correct? Now what we see here is that for some other value, the function value is 10, higher than 8. Do you see that? Now since we know that at critical point, let me write down this, it's very important to understand. So at critical number, we have an extrema. Is that okay? Extrema. Now that is a check. So with this check, we know 8 is less than 10, and therefore this is a minimum. Do you see that? So you can take some other value to justify that the value which you have found is indeed a minimum. So that minimizes. So I hope that part is absolutely clear. I didn't do this in the first example. I may not do it in the other examples also, but that is how you should be doing and checking whether it really minimizes as asked for in the question or maximizes as asked for the question in the given situation. I hope that point is well taken. Thank you. Let's now move on with question number 3. Here is the third example. We'll maximize the function f of xy equals to e to the power xy with the constraint x squared plus y squared equals to 8. So what we are given here is the function in two variables, which is e to the power of xy. So if I take the partial derivatives, then I have f of x as e to the power of xy times derivative of the exponent, which is y. And similarly, f of y will be x times e to the power of xy. Correct? Now if you look at the constraint, which is g of xy, that is equal to x square plus y square minus 8. So g of x, the partial derivative with respect to x will be 2x, and partial derivative with respect to y will be 2y. Now using the Lagrange's equation, the multiplier lambda, we get that y e to the power of xy should be equals to 2x times lambda. So let me write this as 2 lambda x. Is that okay? Similarly, for the next part, we have x e to the power of xy equals to 2 times lambda y. Correct? So we get Lagrange's multiplier equation here. Now we have to solve this equation. The best way to solve this equation will be, let's say, this is our equation 1 and this is our equation 2. So what I do here is that I do equation 1 divided by equation 2. Right? So if I divide these two equations, let's say, as you can see here, what I'm going to do here is I'm going to divide one by the other. So if I do that, 2 lambda cancel out, exponents cancel out, we get y over x equals to x over y. You get an idea, right? So let me show you here. So what we are doing now is we are doing equation 1 divided by equation 2. Perfect. So when I do that, let me use another ink. So when I do that, I get y over x equals to x over y, correct? Since these terms, 2 cancels, lambda cancels. Do you see that? This cancels. Do you see that? So that is why. And that gives you the result, which is y squared equals to x squared. Do you see that? Y squared equals to x squared. Now, we have a constraint, which is x squared plus y squared equals to 8. Correct? So if I substitute y squared equals to x squared here, I can solve for x. Perfect? So that's what I will do. So now I will substitute this particular condition into my equation. Perfect. So I'll write x square plus, instead of y square, I'm writing x square equals to 8, and that gives me 2x squared equals to 8, or x squared equals to 8 divided by 2, which is 4, or x is equals to plus minus 2, square root of 4 with positive and negative. So we get two values for x, plus minus 2. Do you see that part, right? So we get two different values, plus minus 2. Now since y squared is equals to x squared, so for these two different values we can get the value of y also. So basically what we have is, we have x, so the function, basically we got a couple of values here, plus minus 2 and plus minus 2. Both x and y values are either combinations of these. Do you understand? These are combinations for these, right? So we get both x minus 2, and now we need to maximize the function. The idea is we need to maximize the function, correct? So the idea is that we should find the value of this function for different combinations of which means it could be 2 with 2, it could be 2 with minus 2, it could be minus 2 2, or it could be minus 2 minus 2. Do you see? These are all the combinations which you could try. Now since we are assuming that both x and y are positive, so we are using the value 2 2. You get an idea, right? So both x and y are positive. So let's use the value of 2 2 and then figure this out. Now so that means f of 2 2 is equal to e to the power of 2 times 2, correct? Which is e to the power of 4. So that becomes your maximum value. Now how do you say that this is maximum value? Well, if you consider any other point, or in this case, even if you take one as positive, the other one as negative, you get a negative power. For example, if you take 2 minus 2, you get e to the power of minus 4, right? Which is less than e to the power of 4. So what we have here really is a maximum value. Is that okay? Does it make sense to you? So, or you could take some other value and then figure it out that this is indeed the maximum value. So I hope the steps are clear to you. So the idea is find the partial derivatives of the function and the constraint and equate the two with Lagrange multiplier, solve for the values. Is that okay? And then find your answer. Well, in this case, we could find lambda by, now you could find lambda here because you know x is equals to y, so lambda will be equals to, so let's find lambda also. Now from here, okay, let's continue. So the lambda will be equals to, in this particular equation, we are writing 2 for, we are writing 2 2 as our points, right? So we have lambda equals to, let's say 2 times e to the power of 4 divided by 2 times 2, right? That gives us e to the power of 4 over 2, correct? So if I substitute x as 2, y also as 2, correct? In that case, this 2 and 2 cancel, and 2 times 2 is 4, so we get lambda equals to e to the power xy over 2. So that becomes the value of lambda, correct? So that becomes the multiplier. So I hope that is clear, okay? Now let's move on to the last and the fourth part of this set. Here is the last part of our question. We need to maximize fxy equals to the square root of 6 minus x squared minus y squared with the constraint x plus y equals to 2. You can actually pause the video, solve this question on your own, and then look into my suggestions. Now we'll begin as we did last time with our function, which is 2 variable square root of 6 minus x squared minus y squared. Partial derivative of this function with respect to x will be, so this is a square root function, so it'll be half of square root of all this, which is 6 minus x squared minus y squared, times derivative of this function, which is minus 2x, correct? Now that could be simplified, so you could write this as 2 and 2 cancel, minus x over square root of 6 minus x squared minus y squared. Perfect. Similarly, I could write the partial derivative with respect to y as minus y over square root of 6 minus x squared minus y squared. Correct. Now the constraint given to us is g of xy as equal to x plus y minus 2. So g of x is equals to 1 and g of y equals to 1. So if I equate, which is f of x equals to lambda g of x and f of y equals to lambda g of y, I get two equations, correct? So I'll write down those two equations and then solve them. So basically, we have this term as equals to lambda, right? This is f of x, correct? And this term is equals to g of x is 1. That means f of x is lambda, correct? So we have minus x over square root of 6 minus x squared minus y squared equals to lambda, and also minus y over square root of 6 minus x squared minus y squared equals to lambda. So we get our equations, equation number 1 and equation number 2. Now we need to solve for the variables here. So how do we do it? One way is we could divide one by the other. So if I do equation 1 divided by equation 2, lambda lambda cancels, the square root parts cancel, correct? So what do we get? We get x over y equals to 1, or we get x equals to y. Is that okay? So we get x equals to y. So since x is equals to y, we can find both x and y. We can also find lambda, and all these variables can now be easily found, correct? So this time I'm using the fourth method of really finding x, y, and lambda. So the idea is, since x equals to y, we'll begin with our constraint equation, which is x plus y equals to 2. We know x equals to y, so we have x plus x equals to 2, or 2x equals to 2, or x equals to 1, and y is also equals to x, which is also equals to 1, and the critical point therefore is 1, 1, correct? So the critical point is 1, 1. To find lambda, which is the multiplier, you can use any of these equations, correct? So we get lambda equals to, if I write 1 here, I get minus 1 over square root of 6 minus 1 minus 1. Is it okay? So that becomes the value of lambda, as this is minus 1 over square root of 4, which is 2, right? Or we should say half is our multiplier. Is it okay? So for this particular question, we get the value of lambda as half, right? And the values are x1. We can now find the value of maximum, which is 1, 1. So if I substitute 1, 1 here, I get square root of 6 minus 1, which is square root of 6 minus 2, which is square root of 4, which is 2 for us. Is that okay? So we get the value of 2 as the maximum for the given function. Now to show that this is indeed the maximum, what you can do is you can try values like, you know, the constraint is 1, 1 equals 2. You can take y as 0 and x as 2. So if I substitute 0, so to test, what we can do is, so to test whether this is indeed a maximum, we'll try the point, let's say 0, 2. Is it okay? If I try the point 0, 2, what do I get? I get square root of 6 minus 0 square minus 2 square, which is square root of 2, right? And since we know that 2 is greater than square root of 2, critical point is a maximum. So with a test point, so we know that the critical point is maximum. So the critical number is a maximum. Does make sense to you, right? So that is how you could actually solve such questions. And I hope with these 4 examples, you can begin solving questions with Lagrange multiplier with one constraint. Thanks a lot. Feel free to post your suggestions and questions. All the best.